Earth is trapped inside a cosmic void, and it's changing everything we know. There is a question that most people never think to ask. Not where did the universe come from? Not how old it is. Not how big it is. Those questions have answers, or at least working models, that most scientists can broadly agree on, while disagreeing about the details in the specific, productive way that science disagrees about things. The question nobody thinks to ask is simpler and more disorienting than any of those. Where exactly are we? Not in the solar system sense, not in the galaxy sense. In the largest sense, in the sense of, if you could pull back far enough to see the entire observable universe laid out like a map, a three-dimensional structure of filaments and walls and clusters and the vast dark spaces between them. Where on that map would a small blue planet with 7 billion people on it actually be located? The answer that modern astronomy has slowly, uncomfortably assembled over the last decade is this: we are inside a hole, not a black hole, not a wormhole. Something in some ways more unsettling than either of those things, because it is not dramatic and it is not violent, and it does not announce itself with any of the visual intensity that science fiction has trained us to associate with cosmic danger. We are inside a void, a region of space approximately 2 billion light-years across, where the density of matter is roughly 20% lower than the average density of the universe. A cosmic underdensity so large that if you tried to draw it to scale on a piece of paper where the observable universe was the size of a football field, the void would be larger than a tennis court. And the Earth, the Sun, the entire Milky Way galaxy, every star you have ever seen with the naked eye on the clearest night of your life, all of it sits somewhere near the center of this absence. This is the story of how we found out, what it means, and why the answer to where we are might be the reason we have been getting the universe wrong this entire time. The universe is not smooth. The first thing you need to understand is that the universe on the largest scales is not evenly distributed. This is not obvious. It was not always known. For a significant portion of the history of modern cosmology, the working assumption was that matter in the universe was roughly uniform. That if you looked at a large enough volume of space in any direction, you would find roughly the same amount of stuff. Galaxies, dark matter, gas, the whole inventory of the cosmos spread out with the kind of statistical evenness that you would expect from a universe that began in a single explosion and expanded outward in all directions at once. That assumption turned out to be wrong. What astronomers found, as telescopes became powerful enough to map the distribution of galaxies across hundreds of millions and then billions of light-years, was that the universe has structure. Enormous web-like structure that nobody had predicted with the precision that observation eventually revealed. Galaxies cluster together into groups, groups cluster into clusters. Clusters connect through long filaments of gas and dark matter that stretch across hundreds of millions of light-years, forming what cosmologists call the cosmic web, a structure that looks, in three-dimensional maps, something like a vast network of intersecting threads with enormous dark spaces between them. Those dark spaces are the voids. They are not empty in the absolute sense. There are galaxies inside them. There is gas. There is dark matter. But the density of all of those things is significantly lower than in the filaments and walls and clusters that define the rest of the cosmic web. Voids are the negative space of the universe, the places where the universe is not or is less or has been pulled away toward the denser regions surrounding it by the relentless arithmetic of gravity over billions of years. They were known to exist. They had been catalogued and studied and mapped with increasing precision as observational technology improved. The Boötes void, discovered in 1981, stretching approximately 330 million light-years across, was for a long time considered one of the most striking examples, a region so empty compared to its surroundings that when astronomers first measured it, some of them questioned their own data. What nobody had seriously considered was that we might be inside one. Keenan, Barger, and Cowie. In 2013, 3 astronomers at the University of Hawaii published a paper in the Astrophysical Journal that would take several years to fully register in the broader scientific conversation, but that contained, buried in its methodology and data tables, one of the more quietly staggering findings in recent cosmological history. Ryan Keenan, Amy Barger, and Lennox Cowie were mapping the distribution of galaxies in the local universe. Local in cosmological terms meaning within a few billion light-years, using infrared observations that allowed them to count galaxies across a range of distances with more precision than previous surveys had achieved. What they found was a systematic underdensity, starting from our location and extending outward in essentially every direction they looked. There were fewer galaxies than the models predicted. Not dramatically fewer, not the kind of difference that jumps off the page immediately, but consistently, persistently, measurably fewer. The density of matter in our local region of space was approximately 20% lower than the cosmic average. They named it the KBC void after their initials, 2 billion light-years across, the Milky Way sitting somewhere in the interior. The paper did not make the front page of newspapers. It did not produce the kind of immediate cultural moment that discoveries about black holes or gravitational waves tend to produce. It was a careful, methodologically rigorous piece of astronomy that joined a growing body of evidence suggesting something about our location in the universe that was, once you sat with the implications long enough, genuinely difficult to absorb. We are not on the edge of the void looking in. We are on the inside looking out. Everything we have ever measured, every observation ever made from the surface of this planet or from any telescope ever placed in orbit around it, has been made from inside a 2 billion light-year underdensity in the fabric of the cosmic web. And that location, it turns out, may be distorting everything, the crisis at the heart of modern cosmology. There is a number at the center of modern cosmology called the Hubble constant. It measures the rate at which the universe is expanding, specifically how fast galaxies are moving away from each other as space itself stretches. It is one of the most fundamental numbers in all of physics. It appears in calculations about the age of the universe, its ultimate fate, the behavior of dark energy, the geometry of space-time on the largest scales. Get the Hubble constant wrong, and a significant portion of modern cosmological theory is wrong with it. For most of the 20th century, measuring the Hubble constant was one of the central projects of observational astronomy. It is harder to measure than it sounds, because you cannot simply watch a galaxy move and time it with a stopwatch. You have to infer distances using what astronomers call standard candles, objects whose intrinsic brightness is known, so that their apparent brightness in the sky tells you how far away they are. The precision of the Hubble constant measurement depends entirely on the precision of those distance measurements, and for decades the precision was not good enough to settle the debate. In the last 20 years, it has gotten good enough, and what precision revealed was not agreement. There are two primary methods for measuring the Hubble constant. The first uses the cosmic microwave background, the faint afterglow of radiation left over from the early universe, measured with extraordinary precision by satellites like the Planck Observatory, combined with the standard model of cosmology to calculate what the expansion rate should be today. The second uses direct observations of standard candles like Cepheid variable stars and Type Ia supernovae in nearby galaxies to measure the expansion rate as it is today directly. The two methods produce different answers. Not slightly different. Different enough that the scientific community has given the discrepancy its own name: the Hubble tension. The direct measurements consistently produce a higher value for the expansion rate than the early universe measurements predict. The gap between them has grown as the measurements have gotten more precise, which means it is not a measurement error that better instruments will resolve. It is a real discrepancy, and nobody knows why. There are several competing explanations: new physics beyond the standard model, modifications to the theory of dark energy, systematic errors in the distance ladder that haven't been identified yet. And then there is the KBC void. The void as an answer. The logic is elegant and deeply uncomfortable at the same time. If the Milky Way is located inside a large underdensity, a region where matter is 20% less dense than the cosmic average, then the gravity of the denser regions surrounding that void would be pulling matter outward, toward the walls. Galaxies inside the void, including the ones we use to measure the local expansion rate, would be experiencing an additional outward push on top of the universal expansion driven by dark energy. From our perspective, inside the void, galaxies would appear to be moving away from us faster than they actually are moving away from the average point in the universe. We would measure a local expansion rate that is inflated relative to the true global rate. which is exactly what the Hubble tension shows. The local measurements, the ones made using standard candles in nearby galaxies, all of which are also inside or near the KBC void, are higher than the global measurements derived from the early universe, consistently, persistently, by exactly the kind of margin that a large local underdensity might be expected to produce. A 2020 paper by Hochheit and Barger calculated that if the KBC void is real and has the properties that the data suggest, it could account for a significant portion of the Hubble tension without requiring any new physics. The void itself, the simple fact of our location inside an underdensity, could be the explanation for one of the most troubling unsolved problems in modern cosmology. Not exotic new particles, not modifications to the laws of physics. Just the fact that we are measuring the universe from inside a hole, and the hole is bending our measurements in a way we did not account for. This is either a profoundly satisfying resolution to a major scientific problem, or the beginning of a much deeper question about how many other things we are measuring wrong for the same reason. It is possibly both. What the void is not. It is worth being precise about what living inside a cosmic void does and does not mean, because the word void carries connotations that the scientific reality does not entirely support. The KBC void is not a region of absolute emptiness. There are galaxies inside it, including the Milky Way and the dozens of galaxies in our local group, and the hundreds in the Virgo supercluster. There is gas and dark matter and the full complement of cosmic ingredients. The underdensity is a statistical property. Matter is less concentrated here than in the walls and filaments surrounding the void, but it is not absent. The void is also not dangerous in any direct, immediate sense. It does not exert harmful forces on the solar system. It does not affect the sun's output or the Earth's orbit or the conditions for life on this planet. We have been inside it for the entire history of life on Earth, for the entire history of the planet itself, and the consequences for biological evolution have been exactly zero. What the void affects is epistemological, not physical. It affects what we can know and how accurately we can know it. It is a filter through which every observation we have ever made of the universe has passed, subtly distorting the picture in ways we are only beginning to understand. The danger of the KBC void, if danger is even the right word, is not that it will do anything to us. It is that it has already shaped everything we think we know. The deeper problem. There is a principle in cosmology called the Copernican principle. It states, in its broadest form, that the Earth does not occupy a special or privileged position in the universe. We are not at the center. We are not in a unique location. We are, statistically speaking, typical, a planet around a typical star in a typical galaxy in a typical region of space. The KBC void complicates this in an interesting way. On one hand, voids are not unusual. They are a fundamental feature of the cosmic web. If you were to place a point randomly within the observable universe, you would have a reasonable probability of landing inside a void, because voids collectively occupy the majority of the universe's volume, even though they contain a minority of its mass. Being inside a void is not in that sense a particularly special position. On the other hand, being inside a void of this size, 2 billion light-years across, one of the largest underdensities ever mapped, may not be typical at all. Some analyses suggest that the KBC void is larger than standard cosmological models predict voids should be, which would make our location not just inside any void, but inside an anomalously large one. The question of whether the KBC void is consistent with standard cosmology or represents a genuine anomaly is still being actively debated. If it is an anomaly, then the Copernican principle is under pressure in a new way. We would not be at the center of the universe in the old geocentric sense, but we would be in a statistically unusual location, inside a structure that standard models suggest should not quite exist at this scale, measuring a universe whose expansion rate appears inconsistent with its own history for reasons that may ultimately come down to where we happen to be. We would be typical in our cosmic irrelevance and atypical in our cosmic position at the same time, which is, in a very specific way, exactly the kind of answer that the universe seems to prefer. The map we cannot step outside of every map is made from somewhere. This is a statement so obvious that it barely registers as meaningful, until you apply it at the scale of the observable universe and consider what it actually implies. Every measurement ever made of the cosmos, every redshift, every distance calculation, every mapping of the large-scale structure, every estimate of the Hubble constant, every model of dark energy has been made from a single location. One planet, one solar system, one galaxy. One position within the cosmic web that we did not choose and cannot change. We cannot step outside the map. We cannot find a vantage point from which to see our own position objectively. We are always inside the thing we are trying to describe, and the thing we are inside of is, as it turns out, a 2 billion light-year underdensity that may be distorting our view of everything beyond it. This is not a reason for despair. Science has always worked this way. Building models from inside the system being modeled, correcting for known biases, testing predictions against observation, revising when the data demands it. The discovery of the KBC void and its potential role in the Hubble tension is not a failure of cosmology. It is cosmology working exactly as it is supposed to work. Finding the places where the current model doesn't quite fit and interrogating them until they yield something true. But it is a reminder of something that the history of astronomy has demonstrated repeatedly, and that we seem to need to relearn at every scale. Where you stand determines what you see. For centuries we thought we stood at the center of everything. Then we learned we were peripheral. Then we learned we were typical. Now we are learning that typical may have been too comfortable a conclusion, that our specific location within the large-scale structure of the universe has been shaping our measurements in ways we are only now beginning to account for. The universe is approximately 93 billion light-years across in the observable direction. The KBC void is 2 billion light-years across. The Milky Way is 100,000 light-years across. The distance from the Earth to the Sun is 8 light-minutes. We are an almost incomprehensibly small thing, located inside an absence, trying to measure everything from here. And the most honest thing that modern cosmology can say about that project is this: we are getting better at it. We are identifying the ways that our location distorts our view. We are building corrections into our models. We are asking, for the first time with real precision, not just what the universe looks like, but what it looks like from here. And what the difference between those two questions might mean for everything we think we know. The void is not the end of the story. It is the discovery that the story is more complicated than we thought, which is, in the history of science, how the most important chapters always begin.